Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Marc Heyberger from Cadence. Going to talk today about new challenges in sign-off. Marc, engineers have always been nervous about signing off on designs and sending them to manufacturing. So, did they do everything right? Is there sufficient coverage? Is there something that's going to go wrong down the line? When are they actually going to push that button that says, okay, send to manufacturing? But it's also becoming much more difficult. There's a lot more things that can go wrong when you get to advanced nodes and in multi-die assemblies, which greatly increase the complexity of these designs. So, how is this impacting what engineers are doing? How do they know when it's time to send something to manufacturing?
So definitely design size is increasing, especially in the AI space, where a few years ago we were wondering ourselves, how would we really handle a 1 billion instance design? It was just crazy thinking about that. But guess what? Lately, now today, design with just a single die level can be easily 2 billion instance already to be handled.
Marc, let's take a closer look.
Yes, sure.
Marc, what are we looking at?
While design size is increasing, as I explained, we have actually some good opportunity here for EDA tools. First of all, those designs are highly replicated modules. So this allows actually the designer to perform block level optimization, subsystem level optimization, and then full chip optimization. Now, with this complexity comes also the challenge, meaning that turnaround time to deliver chips has not increased, although the chips are more complex. Tools have many more features to handle all the latest technology, so the flow is still as complex as in the past, but with bigger designs. And of course, resource in terms of human and machine is not increasing either. So there's a big demand on the market to improve the productivity of the entire flow. And that's where EDA tools have to play a big role.
Are the tools keeping up with the complexity? So, is the time that it takes to design and make sure that it's good enough to send to manufacturing, has that increased or is it still the same?
There are definitely new challenges that are coming to us. First of all, is the netlist size, as I mentioned earlier, is increasing. This is mostly the case because AI chips have hugely highly replicated modules. It means a given module, given functionality, would be replicated thousands of times. So that's one aspect. The second aspect, it is on the physical side, meaning the information that needs to be loaded to handle all the physical awareness at sign-off stage. And that brings challenge when assembling all those physical data. And then it comes to the sign-off and timing flow. There, customers are now adopting approach what we call bottom-up, meaning that they have to clean up everything the single block level first, and then they will build up the hierarchical flow. So when we see an entire implementation to sign-off flow, it always starts with block level implementation. And already at that stage, customer would now do ECO and timing closure using a sign-off timing to make sure it is clean inside the partition. Then, as we move on to the tape-out flow, those different partitions are assembled and that creates a subsystem. This subsystem, as you can see, already contains multiple replication of the same partition. And there, the user will perform now inter-partition timing and power closure, because that's where new violation might be seen, while inside the partition, we know it is clean from the previous step. And so on, when assembling multiple subsystems, you get to a cluster level. Again, the same kind of analysis and optimization happening this time inter-cluster. And then again, at full chip, once you assemble all those clusters to create your 1, 2, 3 billion instance design, again, you will see that the user has to optimize between the cluster. And all that, even on this picture, you can see that those partition I showed on the left side are already replicated many, many times. Then that's the end of the automated flow. After that, the user will find out, okay, I still have a few remaining timing violation that prevents me from doing a sign-off. So then I would go and load only that part of the design and do a surgical manual ECO to fix the remaining violation. And at the end, when the designer is happy with what he sees, then he will perform a full flat timing analysis. So that's the entire flow, how user is handling timing closure.
Typically, engineers have done this by breaking things down into digestible pieces. This whole thing has to be looked at as a whole as well as the individual pieces too, right? How has that changed?
Yes, that's right. So for that, as you just said, in the past, user would always like to go full flat. Okay, that's the easiest. You have as an entry point a flat timing constraints. You assemble your different netlist from the different block level, and then you perform flat timing analysis. Unfortunately, this brings new challenge for those 1 billion or bigger type of design. And for that, either you continue using this approach, but you require distributed sign-off timing analysis tool, which is able to cope with such increased number of instances. Or what we see now is higher demand on hierarchical timing analysis, where, as you just mentioned, user can divide and conquer, meaning it can perform full chip level timing analysis by not loading actually the full chip netlist. And that is key to be able to perform faster iteration. And likewise, the user can also decide to create a context for one of these partitions to perform analysis at block level using the timing from the full chip. So there's a little bit more data management, but that allows to go through the big chip design sign-off.
So what happens when you get into multi-die assemblies? And particularly what's coming down the pike here is full 3D IC. We've never seen this before, much more complicated than what we've seen with 2.5D, right?
3D IC brings a whole set of new challenge. First of all, we have the same challenge as at die level, meaning that die level are getting bigger, but now you assemble multiple dies. When you assemble multiple dies, obviously, there will be a challenging timing path between the die. And to analyze that, you need to analyze the different variation of each die versus each other die. So that leads to a corner explosion. And there are other side effects like coupling between dies and thermal variation across die. So for that, EDA tools are getting improved to handle that nicely. So the first thing that you would always want to do is to reduce the complexity of having to time so many different variation. We would apply some engine called rapid automated inter-die analysis. This will reduce the set of timing views to the minimum one that would cover the inter-die. And on top of that, to avoid timing each of those views independently, we can apply technology like multi-mode, multi-corner timing architecture so that one single session would time multiple views at a time. The size is really one of the challenge. So then we can apply a technique we just talked previously called hierarchical timing analysis, where each die would actually be modeled using a boundary model. So you have only the shell logic of each die that anyway would be the logic talking to the other die. And that's how we can reduce the size seen by the sign-off STA tool. So that's using boundary model. And on top of that, you would apply the characteristics that would model thermal variation using thermal map to perform a thermal aware ST analysis. So those are the two fixes. Now on top of that, now you would see some timing violation that you actually need to fix. And that's where a Certus comes into play. Certus will take as input this 3D IC timing analysis, and at the same time, it will load as Certus client Innovus database that would come from those different dies. And those could be from different technology node. And Certus, with his unique distributed ECO algorithm, is able to cope up with this extra challenge of 3D IC level.
This is a massive challenge. You've really got to do this enormous simulation of and raise up the whole abstraction level, but at the same time you have all these things that are coming in at very small dimensions, right? So you've got potentially 2 nanometer chips in here in addition to older nodes. You've got, and that brings in the variation that, okay, we've got 2 nanometer chips, the variation matters more than it does at some of the older nodes. And then you've got very tight lines and spaces and interconnects. All this stuff has to be looked at as one chip.
Exactly. So all those technology presented here allow the user to still sit into one single cockpit when it comes to timing analysis, but cope with all those extra challenge. And similarly, for the ECO closure, the single cockpit called Certus manage everything for the user. And since each Certus client is independent from all the other Certus clients, it is able to load a different technology node, and there is really no conflict anymore.
So now you have to look at this in multiple dimensions with multi-physics. It's no longer just a single corner case, right, that we used to look at and say, okay, the timing was off slightly here. It's now what caused that timing? How many other components are affected here?
Right. So timing is affected by multiple directions. It can be the air drop, it can be the metal field, it can be the parasitics extraction, it can be thermal analysis, it can be, yes, the voltage in which the chip is operating. So now what we are really seeing is that for the traditional flow where implementation would only see what it has to optimize to get to a place and route database to be given later on for all those sign-off tool that measure all those effects you were just talking about. Now, tools have been improved during the implementation phase to actually take early in the flow the impact of all those new challenge coming with latest technology. So this is actually accessible because all those sign-off tools are now accessible through the engine directly inside the implementation tool. So designer can go and check any type of sign-off analysis being respect to voltage, being respect to thermal, or even any metal field, and can start applying those rules and can start measuring the impact of those rules. And then implementation tool will actually take the right decision so that at the end you get out of that a much cleaner exit to handle all those situations.
So how far along are we at this point? We're just starting to see, are we just starting to see the problems or are we really addressing them?
Oh, we actually start addressing them. The whole idea is to put what we have been able to measure only up to now at the end of the flow, put that early on the flow so that the user can take the right decision and get to a better exit point from the implementation tool to then ease the job at sign-off stage.
Well, 3DIC is basically the ultimate push everything left and extend right simultaneously, right?
Yes, and that brings another challenge that we slightly touched base previously, which is the amount of timing analysis views, right? So for that, EDA tools have been enhanced to get some better reduced set of timing views. So how it works is that tool would actually scan the timing seen per view and then compare that among all the other views. And then there is some proprietary algorithm where the tool will decide, okay, those are the reduced set of timing views that I should consider. And this would still allow me to have full timing accuracy and would also allow me to see the entire cross variation through the chip or just at die level. So that with full accuracy, and that's how we can reduce from several hundred timing views to just maybe 10 or 20 timing views.
So are 3DICs real? Are they coming? We have not seen any in the market yet.
Yeah, well, we are seeing them definitely at our side. Customer are really working on them now. Whether they are ready to productize them, that's not on our side as an EDA company. But surely we are working very hard to allow them to step them out.
How will AI impact all this? We've been hearing about AI, and AI has some problems in terms of hallucinations. You can potentially get wrong results out of some of these things. The way that EDA companies have been dealing with this has been very gingerly looking at it and tightly controlling all the loops in here. But it can be used much more effectively and than what it's been used in the past. What's happening now?
Yeah, that's right. AI is coming in our daily job, definitely as an EDA company. It spans from verification up to silicon qualification. Now, when it comes to the sign-off tool, this is actually quite tricky. So we are taking some cautious steps to go there because sign-off tool must be 100% accurate. Okay, you cannot have any compromise. While on the other hand, you just mentioned AI might not be always fully reliable, might not be fully accurate in the answer it provides. So for that, what we are seeing is AI will help a sign-off tool to improve productivity more than accuracy. And for productivity, AI tools will find out where the script is not optimal, for example, or where the timing constraints can be reduced so that it goes faster. And when it comes to ECO, what we are really envisioning is that the ECO timing closure, the last mile closure I was mentioning earlier, those would actually be driven by AI because AI would actually guide the user on why the remaining violation were not fixed and what could be potential good ECO move to fix those violations. So it's all about productivity, Ed.
Marc Heyberger, thanks for a great explanation.
You're welcome, Ed.